Welcome to 1.2a. This is parent functions. Parent function is the most basic function for a specific type, for a specific function family. And all of the other functions in that family are derived from it. So we're going to look at each function, parent function, write its equation, find critical points, list any special features it may have, graph it, sketch its domain and range. So for the linear function, its parent function is simply f of x equals x. Y equals x. So whatever the x is, the y is the same value. So if x is -5, f of x is also -5. -3, comma -3, 0, 0, 4, 4, and 7, 7. So that line, y equals x, we know goes through the vertex, at through the origin at 0, 0, and its x and its y are equal. So we have a line through the origin with a slope of 1. And here is our line. It does go on forever in each direction. So its domain is all real numbers. Its range is all real numbers. Any special features, it does go through 0, 0, and it does have a slope of 1, and that is just for the parent function. Okay. On the quadratic is a x squared, so f of x equals x squared is the most basic form of that function that qualifies as quadratic. So if we have an x of -3, we have a y of 9. If we have an x of -1, we have a y of 1. 0, 0 squared is 0. 2 squared is 4, and 3 squared is 9. We take the x, we square it, multiply it by itself, get the y. So that quadratic parent function does have a vertex at 0, 0. Okay, 1 squared is 1. 2 squared is 4. 1, 2, 3, 4. 3 squared is 9. 5, 6, 7, 8, 9. And then we know a parabola, quadratic, is perfectly symmetrical. So it's the exact same thing on the other side of the y-axis. And here is our quadratic parent function. So looking at the domain, it does go on forever in each direction, left and right. The range does have a bottom. It does bottom out at 0. That's going to be a bracket because it is used, and it goes up forever. So that's to infinity with a parentheses. Okay, some special features here. The parent function does have a vertex at 0, 0, and it does have symmetry. It is symmetrical over a vertical line. Our next function would be the square root function, and its parent function is simply f of x equals square root of x. So we want to think about numbers that we actually want to take the square root of. If we have a negative number for x, we can't take the square root of a negative number. That's non-real. It's imaginary. We'll deal more with those later. We can take the square root of 0. Square root of 0 is 0. If x is 1, the square root of 1 is 1. I don't really want an x of 2 because I don't want to take the square root of 2. The next number I probably want to take the square root of is 4. And the square root of 4 is 2. The next number, I don't want to take the square root of 5 or 6 or 7. Those aren't going to be nice numbers. But the square root of 9 is 3. So as we plot those points, 0, 0 is our starting value. 1, 1, 4, 2, 5, 6, 7, 8, 9, 3. And we have our square root function. It cannot exist on the left. Cannot exist to the left of 0, 0. Because we cannot, the square root of negative numbers is not real. So that domain is does equal 0, bracket 0 to infinity, parentheses. Same thing on the range. The minimum square root is 0, and it's going to go up to positive infinity. It will go up very slowly, but it will go up. So its special features is that it has a minimum at 0, 0. Minimum value for the parent function would be 0, 0. And there is your square root function. Next, we have the absolute value function. It is f of x equals absolute value of x, the vertical bars. So for the absolute value of x, if we have x as negative 5, the absolute value of negative 5 is positive 5. X is negative 2, for instance. Absolute value of that is positive 2. We can take the absolute value of 0. It is 0. Then the absolute value of 3 would be positive 3. Absolute value of 6 would be positive 6. So absolute value takes any negative number and turns it into positive. Positive numbers stay positive. The absolute value is the distance from 0, so it's the positive value of the number. So in terms of graphing this, absolute value of 0 is 0. Anything on the right, absolute value of 1 is 1, absolute value of 2 is 2. The absolute value of any positive number is that same positive value. Now, on the left, on the negative side, the absolute value of a negative number is it's positive. So absolute value of negative 1 is positive 1. Absolute value of negative 2 would be positive 2. Negative 3, 3, and so on. So we can see the shape we're making here is a V. The absolute value graph makes the shape of a V. Absolute value graph makes the shape of a V. So its domain is all real numbers. We can take the absolute value of any real number. Its range, since absolute value is never negative, absolute value does start at 0 with a bracket. It does continue up to 0, 0. It does have a vertex or a minimum at 0, 0, and it is symmetric. It is symmetric across the y-axis. The y-axis acts like a line of symmetry for that parent function. Now, let's look at an exponential function. For an exponential function, f of x equals something to the power of x. The number we typically use, well, we call it a base to the power of x. Typically, we use 2 to the power of x as the parent function, but any base to the power will work. So if we think about negative values, if x is negative 2, 2 to the power of negative 2, 2 to the power of negative 2 is 1 over 2 to the positive 2, so that's 1 over 4. X is -1. 2 to the -1 is 1 over 2 to the +1. So that's a 1/2. 0, 2 to the 0 power. Any number to the 0 power is 1. Then when X is 1, 2 to the first power is 2. When X is 2, 2 to the second power, 2 squared is 4. And then we do typically use 3 here. 2 to the third is 8. So 3, 8 is another point here. So at -2, we had a y of 1/4. -1 or -1 had a y value of 1/2. 0, 1, 1, 2, 2, 4, and 3, 8. And we can see the curve going on with this exponential function. So it stays really close to this x-axis. Then as it crosses the y-axis, starts going up in a really big hurry. It does go on forever. Okay, if we think about those y values, trying to make those y values negative, 2 to any power, to try to get a negative number, it won't work. 2 to any power will never be negative. So the domain on this, we can use positives and negatives. It is all real numbers. The range here is 0 to infinity. Infinity is always a parentheses. This 0 here, we never equal 0. The range, the y, does not actually equal 0. So from 0 to infinity is your range. So for special features, we do have an asymptote at the x-axis. We do have an asymptote on the x-axis. So we have an asymptote at y equals 0, which is the x-axis. Now, logarithmic function. Logarithmic function would be f of x equaling, I'm doing these in all different colors. So f of x would equal log base b of x. Now, f of x equaling log base b, it's an inverse of the exponential function. It's an inverse of the exponential function. So any x value, okay, if we use log base 2 of x, okay, it's the exact inverse of the exponential function. So where the exponential function was -2 1/4, this would be 1/4, -2. Then 1/2, -1. Then 1, 0. 2, 1. And 4, 2. We're taking the x and y for the exponential and switching them to make the other function. So if we plot these, the x of 1/4 had a y of 2, x of 1/2 had a y of -1, and x of 1 had a y of 0, then 2, 1, 4, 2, and 8, 3. I may not have written that one down. I didn't. 8, 3. So it's the same shape as the exponential, but going the other direction. So this graph has a vertical asymptote at the y-axis. So its special features will be an asymptote at x equaling 0, meaning it is the y-axis that's its asymptote. Its domain cannot touch 0, but it does go up to infinity, and its range would be all real numbers. We'll deal more with the absolute value, with the exponential and logarithmic functions in future units. For now, just recognize the basic shape of those types of functions. Okay. Cubic function. Cubic function is f of x equaling x to the power of 3. Cubing the number raises it to the power of 3. So for that, if we have -2 to the third power, it's -2 times -2 times -2, that's -8. -1 raised to the third power is -1. 0 to any power is 0. 1 to any power is itself. 2 to the power of 3 is 8. So looking at our graph, -2 has a y value of -8, -1, -1, 0, 0, 1, 1, and 2, 8. So here's our function. Here's our function. It's going to go up. It's going to go through the origin in zigzag, and then it's going to keep going up. And there is our cubic function. So its domain, any real number, can be raised to the third power. So its domain is all real numbers. When we look at the range, it does go all the way down and all the way up, so that is also all real numbers. Okay. Any special features, it does have symmetry around the origin, meaning it can be rotated around 0, 0. And it is perfectly symmetrical around the origin. It's around a point. Okay. The next function is the cube root function. And for the cube root function, we want to use x values that we can take the cube root of. So that function would be f of x equaling cube root of x. So we can take the cube root of 0, it's 0. We can take the cube root of 1, it's 1. The cube root of 2, 3, 4, 5, those are not going to be nice numbers. But the next perfect cube is 8, and its cube root is 2. Because 2 to the third power is 8. So thinking of this backwards, the cube root of -1 would be -1. And the cube root of -8 would be -2. So those numbers should look familiar. Those numbers went together in the cubic function. They're just in a different order. So -8, -2, -1, -1, 0, 0, 1, 1, and 8, 2. And our function starts left, goes to 0, 0, zigzags through 0, 0, and continues to the right. So our domain here, left to right, is all real numbers. Our range, bottom to top, this will go all the way to negative and positive infinity. It's going to be slow, but it will get there. So its range is also all real numbers. Yes, you could write that as negative infinity to positive infinity. And if we look at the shape of this graph, it is also symmetrical around the origin. If you rotate it around the origin, it is perfectly symmetrical. Right, our last parent function is the rational function. And this rational function's equation is f of x equals 1 over x. 1 over x. So if x is -4, 1 over x is -1/4. X is -1. 1 over -1 is -1. Now, we do need some fractions on this one, so I'm going to use a -1/2. 1 over -1/2. Remember, 1 over a fraction flips it, so that's -2. If we think about 0, 1 over 0 is undefined. It is not allowed. Not allowed. If we use 1/2, 1 over 1/2 is 2. And if we use +2, actually I'm going to do this. 1 over 1 is 1. And I'm going to go ahead and use +3. 1 over 3 is going to be 1/3. Okay, now that's a lot more points than normal, but you'll see why. So -4, we had a -1/4, -1, -1, 1/2 was a -2. And then we didn't have anything at 0. But then our other points, 1/2, 2, 1, 1, 3, 1/3. No. 3 is 1/3. So the shape of this one is a little different. It is in 2 pieces. It stays just under but really close to the x-axis, curves towards 1, 1, and then curves towards that y-axis and goes straight down. The other piece mirrors it. It stays really close to the y-axis going up, curves at 1, 1, and stays really close to the x-axis as it goes to the right. So this graph has a domain that cannot include 0, 0, cannot include 0. So it goes from -infinity to 0, does not include 0, union 0, not including, to infinity. That includes everything except 0. Now, the range, bottom to top, is going to do the same thing. We did not include x equals 0. And we are not going to include y equals 0. So the range will be the same thing. -infinity to 0, union 0 to infinity. Special features, it has asymptotes. Asymptotes on x-axis and y-axis. So that's y equals 0 and x equals 0 for the equations of those asymptotes. So that is it for parent functions and their domains and ranges. Bye, y'all.